A soft descent into quantum computing, the tiny machines changing tomorrow. Approximately 5,000 words. Settle in. Let everything around you become quiet. We are about to drift, slowly and softly, into a realm that most people only hear about in passing, a place where computers think in ways that feel closer to starlight and probability than to anything metallic or digital. This is the world of quantum computing, a field woven from mathematics, physics, engineering, and imagination. It is a history filled with brilliant scientists, bold ideas, strange phenomena, and technologies so delicate they almost seem like dreams you might forget upon waking. And yet, every year, they become more real. Tonight, we glide gently across a landscape of decades, names, and discoveries, observing how a set of tiny, fragile machines began reshaping our vision of tomorrow. Let the story unfold slowly. Quiet origins, quantum theory before computers. To understand quantum computing, one must float back to the early 20th century, when the universe was still being explained by classical physics, when atoms were imagined as tiny planetary systems and electrons obediently orbited like miniature moons. But in 1900, a German physicist named Max Planck proposed something that cracked open the universe. Energy, he claimed on December 14, 1900, was not infinitely divisible, but came in discrete packets he called quanta. That date is now often considered the birth of quantum physics. In 1905, Albert Einstein built on this idea, showing that light itself behaved like particles, later known as photons. In the 1910s and 1920s, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and Wolfgang Pauli took turns crafting new laws that governed the very small. These laws felt contradictory and poetic. Particles could be in multiple states at once. They could be entangled, behaving as if linked across distances, and observing them changed their behavior. Quantum mechanics was not created for computers. It was created to explain reality. But as the decades passed, clever minds wondered if these strange rules could be harnessed. This slow realization moved gently through the mid-20th century, almost unnoticed, carried by quiet academic conversations rather than the roar of industry. Roman II, classical computing takes shape. Before quantum computing could be imagined, classical computing had to evolve. In 1936, a young British mathematician named Alan Turing wrote a paper titled On Computable Numbers, in which he described a hypothetical machine, now called the Turing machine, that could perform computations using logical steps. This was not yet a computer, but the blueprint of computation itself. The first electronic computers arrived in the 1940s, ENIAC 1945, EDVAC 1949, and UNIVAC 1951. Through the 1950s and 1960s, companies like IBM pushed computer science forward, shrinking machines gradually, introducing new programming languages, and refining architecture. By the 1970s, Moore's Law, announced by Gordon Moore on April 19, 1965, appeared prophetic: more transistors every year, smaller components, faster processors. But beneath the surface of this golden age of miniaturization was a whisper. One day, transistors would be so small that quantum effects would interfere. Classical computing would meet a physical wall. And long before that wall appeared, a different idea had been forming quietly in the background. Roman III, a strange thought appears. Feynman and the early concept, 1981-1985. The spark of quantum computing as a formal concept is usually traced to May 1981, at a conference hosted by MIT and IBM, where the renowned physicist Richard Feynman delivered a talk titled Simulating Physics with Computers. In his charismatic, plain-spoken style, he stated something deceptively simple. Classical computers cannot efficiently simulate quantum systems because nature itself is quantum. If you want to make a simulation of nature, Feynman said, you'd better make it quantum mechanical. This idea landed softly at first, like a pebble dropped into a still pond, but it created ripples that continue to expand today. The next major step came from Oxford University physicist David Deutsch. In 1985, Deutsch published a landmark paper, Quantum Theory, the Church-Turing principle, and the universal quantum computer. He proposed the first formal model of a universal quantum computer, one that could run quantum algorithms just as Turing's machine could run classical ones. The field was still hypothetical, no machines existed, but a theoretical foundation was being carefully laid, one equation at a time. Roman 4. The advent of quantum algorithms, 1990s. The 1990s brought a quiet revolution marked by a series of intellectual breakthroughs. In 1992, at AT&T Bell Labs, physicist Peter Shor developed the first quantum algorithm that could solve a real-world problem exponentially faster than classical computers. His algorithm, presented at the 35th Annual Symposium on Foundations of Computer Science in November 1994, could factor large numbers efficiently. This single achievement suggested quantum computers might one day crack the encryption protecting global financial systems, secure communications, and more. Just 1 year later, in 1995, another scientist at Bell Labs, Love Grover, developed a search algorithm that could scan an unstructured database quadratically faster than classical methods. These discoveries gave quantum computing its first true purpose: speed. Not ordinary speed, but a kind of computational acceleration that seemed almost magical. But still, the machines remained imaginary. Building the impossible. The first experimental quantum bits late 1990s, early 2000s. To turn theory into hardware, scientists needed something new: the qubit. A qubit is the quantum version of a classical bit. Instead of being 0 or 1, a qubit can exist in a superposition, a gentle blend of both states. When entangled, qubits can share information in ways that defy classical intuition. In 1998, two groups independently created the first working 2-qubit quantum computers. One team was led by Isaac Chuang at IBM's Almaden Research Center, and another was led by Neil Gershenfeld and Mark Kubinek at UC Berkeley. These machines used nuclear magnetic resonance NMR, manipulating molecules dissolved in liquid. They weren't practical, but they proved the concept. By the early 2000s, multiple approaches to physical qubits emerged: superconducting qubits, trapped ions photonic qubits, quantum dots topological qubits. Each approach had advantages and limitations. The world's laboratories became quiet experimental battlegrounds, where researchers fought to increase coherence time, reduce noise, and stabilize fragile states. Names like John Preskill at Caltech, Raymond Laflamme at the University of Waterloo, Ignacio Surac and Peter Zoller in Innsbruck, and David Wineland at NIST became central pillars in the field. In 2001, Wineland's team demonstrated a controlled NOT gate using trapped ions, one of the first true logical operations in a quantum system. The impossible was becoming possible, one delicate experiment at a time. The 2000s, companies enter the scene. By the early 2000s, commercial interest began stirring. In 1999, D-Wave Systems was founded in Vancouver by Geordie Rose. Their goal was ambitious: build quantum computers using superconducting flux qubits. By 2007, D-Wave announced what they claimed was the first commercial quantum computer, the D-Wave 1, though its quantum nature and performance were heavily debated. Over time, the company refined its technology, demonstrating increasing levels of quantum annealing capability. Meanwhile, IBM continued building superconducting qubits. NIST refined its trapped ion systems. The University of California, Santa Barbara, home to physicist John Martinez, advanced superconducting quantum circuits. The Max Planck Institute in Germany continued photonic research. These groups were like early navigators mapping a strange new continent. The details were blurry and often contested, but something new was emerging. Roman 7, 2010-2016, the first quantum era takes shape. As the 2010s dawned, quantum computing shifted from concept to competition. In 2011, researchers at UXP demonstrated the world's first quantum processor with error correction components. This was key. Quantum mechanics is incredibly fragile, and errors creep into every calculation unless corrected. In 2013, Google entered the field by launching a quantum artificial intelligence lab in partnership with NASA and the university's Space Research Association. They purchased a D-Wave machine, though the debate around its usefulness continued. A slow, steady rise continued, with breakthroughs happening year after year. 2011, the first programmable 2-qubit photonic processor. 2014, MIT researchers demonstrate silicon-based quantum chips. 2015, Google improves superconducting qubit fidelity. 2016, IBM opens the first cloud-accessible quantum computer. This last event in May 2016 was a turning point. IBM had placed a small quantum processor, 5 qubits at the time, on the cloud under the name IBM Quantum Experience. Anyone could log in and run a quantum circuit. The field was no longer limited to elite labs. The world had taken its first collective step into quantum computing. Roman 8, 2017-2020, Quantum Supremacy and the Modern Race. The most public milestone during this era arrived on October 23, 2019, when Google published a paper in Nature claiming it had achieved quantum supremacy, the point where a quantum computer performs a task impossible for classical machines in a reasonable time. Using a 53-qubit processor named Sycamore, Google researchers Junho Kim, Charles Neal, Pedram Raushan, John Martinez, and others performed a complex sampling problem in 200 seconds. Google asserted that the most powerful classical supercomputer would need 10,000 years to match it. This announcement ignited intense debate. IBM quickly released a rebuttal, arguing the computation could be done on a classical supercomputer in 2.5 days rather than millennia. But regardless of the dispute, quantum computing had entered public consciousness with force. Other developments during these years included Intel releasing its 49-qubit chip, Tangle Lake, in 2018, RightD Computing building a cloud platform for hybrid quantum classical systems, IonQ, founded in 2015 by Chris Monroe, and Youngsang Kim emerging as a leader in trapped ion computing, Xanadu in Toronto developing photonic quantum processors. Meanwhile, governments accelerated national programs. In December 2018, the United States signed the National Quantum Initiative Act. The European Commission launched the quantum flagship in 2018 with a 10-year, Euros 1 billion mandate. China dramatically expanded its quantum research centers, most notably in Hefei. Quantum computing was no longer fringe, it was a global race. Roman 9, the 2020s, toward fault tolerance and practical use. As the 2020s unfolded, progress shifted from building bigger machines to building better ones. The focus became error correction, noise mitigation, scalable architecture materials, science cryogenic engineering, quantum networking. In 2021, Google announced a plan to build a 1 million-qubit, error-corrected quantum computer by the late 2020s or early 2030s. IBM published its own roadmap in 2020, forecasting increasingly large processors, 127 qubits in 2021, 433 qubits in 2022, 1121 qubits in 2023. These milestones were largely met, showing unusually disciplined progress for such a difficult field. IonQ, using trapped ions, produced some of the highest fidelity qubits in the industry. PsiQuantum, founded in 2016 by Jeremy O'Brien, pursued a fault-tolerant photonic approach, aiming for 1 million qubits via silicon photonics. Honeywell Quantum Solutions, later merged with Cambridge Quantum to form Quantinuum in 2021, demonstrated some of the lowest error rates ever recorded. Quantum computers were becoming real tools, though still fragile and experimental. During this period, researchers also created record-breaking entanglement demonstrations. In 2022, a team at Delft University demonstrated quantum teleportation between non-adjacent qubits in a network, a step toward a quantum internet. In 2020-2023, Chinese researchers in Hefei repeatedly improved photonic quantum sampling records. Each experiment was like a bright spark in a slowly dawning world. X. How quantum computers actually work. To appreciate these machines, one must move slowly through the concepts. A qubit is not merely a 0 or 1. It is a state on a Bloch sphere, a smooth, continuous surface where all possible quantum states reside. Superposition allows a qubit to be both 0 and 1 simultaneously, with probabilities defined by its amplitudes. Entanglement links qubits so tightly that measuring one instantly affects the state of another, regardless of distance. Quantum gates, rather than flipping bits, rotate these states or entangle multiple qubits. Quantum algorithms guide these operations to exploit quantum interference, allowing incorrect solutions to cancel out and correct ones to remain. Measurement collapses the state into classical information, yielding answers. Quantum computing is therefore not faster because it tries all possibilities at once, though that metaphor is tempting, but because it uses interference to isolate the correct solutions with far fewer steps. It is subtle, mathematical, and deeply beautiful. Roman 11, applications whispering on the horizon. Although fault tolerance remains a challenge, quantum computing holds promise across numerous domains. In chemistry and materials science, quantum systems can simulate molecules with high precision. The dream of modeling complex molecules, such as nitrogenase, the enzyme that fixes atmospheric nitrogen, has been alive since the 2010s. One of the earliest proposals, made in 2014 by Ilan Aspiruguzek, suggested that quantum computers could revolutionize drug discovery. In optimization, quantum techniques may enhance logistics, scheduling, or portfolio design. D-Wave pursued this field aggressively, attracting clients like Volkswagen and NASA. In cryptography, post-quantum algorithms are being designed to withstand Shor's algorithm. In 2016, the U.S. National Institute of Standards and Technology (NIST) began the standardization process, culminating with chosen algorithms in 2022. In artificial intelligence, hybrid models combining quantum circuits with classical neural networks began emerging around 2019-2020. Each of these applications is still in early stages, more promise than product, yet the trajectory is unmistakable. Roman 12, the human side, the scientists behind the work. Quantum computing is also a story of people, quietly devoting decades to work that often seemed impossible. David Deutsch at Oxford, whose 1985 paper laid the foundation. Richard Feynman, whose 1981 challenge inspired generations. Peter Shor, whose 1994 algorithm electrified the field. Love Grover, whose algorithm broadened the scope of quantum speedups. John Preskill at Caltech, who coined quantum supremacy in 2012. David Wineland, whose trapped ion work earned him the 2012 Nobel Prize in Physics. Ilan Aspiruguzek, who connected quantum computing with chemistry. John Martinez, who led Google's 2019 quantum supremacy experiment. Michelle Simmons in Australia, who pioneered atomically precise quantum fabrication. Stephanie Simmons, advancing silicon spin qubits. Andrea Morlow, working with single-atom qubits in silicon. Charles Bennett at IBM, who co-developed quantum cryptography in the 1980s. These individuals and hundreds more form a quiet tapestry of ingenuity. Their work waits patiently in journals, conference proceedings, and lab notebooks, each thread contributing to the evolving world of quantum technology. Roman 13, the delicate machines of today. Modern quantum computers, as of the mid-2020s, exist mostly inside cryogenic refrigerators that stand taller than a person. These refrigerators, called dilution fridges, chill their contents to temperatures around 10-15 millikelvin, colder than outer space. Inside them sit fragile quantum processors, often made of superconducting metal patterned onto silicon. These chips are connected by gold-plated wires, coaxial cables, and microwave circuitry, forming what looks like a chandelier of cables descending from layers of golden plates. Other systems, for instance, trapped ion machines, hold electrically charged atoms suspended in electromagnetic fields, controlled by finely tuned lasers. Photonic systems use networks of beam splitters, interferometers, and single photon detectors. Each architecture is an engineering marvel, requiring exquisite sensitivity and control. These machines are not yet ready to replace classical computers. They are closer to early aircraft, capable of flight, but delicate and limited. But history teaches us that delicate things can reshape the world if given time. Roman 14, the road ahead, fault-tolerant quantum computing. The holy grail is fault tolerance, the ability to perform long, reliable computations despite noise. To achieve this, scientists rely on quantum error correction codes. One of the most famous is the surface code, introduced by Alexei Kiriv in 1997 and refined through the 2000s. It requires many physical qubits to protect a single logical qubit. Estimates vary, but a single logical qubit might need hundreds or even thousands of physical qubits. The world's most advanced machines today have between 50 and 1,000 qubits. A full fault-tolerant computer might require millions. And yet the field is confident, progress is steady. IBM's 2022 Osprey processor reached 433 qubits. Google's physical qubits have steadily improved in error rates. Quantinuum demonstrated the first repeated quantum error correction cycles in 2021-2022. IonQ reported record gate fidelities across multiple years. Quantum continues pursuing an industrial-scale photonic architecture using semiconductor fabrication. Some predictions place fault-tolerant quantum computers in the 2030s. Others expect breakthroughs sooner or later. As with any frontier technology, timelines are fluid. But the trajectory is unmistakably upward. Roman 15, why quantum computing matters. In whispered tones, scientists describe quantum computing as a new phase of computational capability, not merely faster, but fundamentally different. It invites us to rethink how we simulate nature, how we design medicines, how we secure digital systems, how we model global markets, how we explore optimization landscapes, how we understand information itself. Classical computers transformed the 20th century. Quantum computers could transform the 21st, not by replacing classical systems, but by augmenting them, forming hybrid architectures that blend deterministic logic with quantum probability. In many ways, quantum computing is not about speed, but insight. It allows us to peek into regions of mathematics and physics that were once completely inaccessible. Roman 16, a soft conclusion, the machines changing tomorrow. Quantum computing's story is not finished. It is still unfolding, quietly, methodically, patiently. It is the slow-building crescendo of a global collaboration that spans decades, disciplines, and continents. From Max Planck in 1900 to Richard Feynman in 1981. From David Deutsch in 1985 to Peter Shor in 1994. From the first 2-qubit machines in 1998 to cloud computing in 2016. From Google's 2019 announcement to the ever-evolving machines of the 2020s. Every step is small, yet each builds on the last, forming a delicate ladder toward another level of understanding. The future quantum computers may simulate life, model new materials, crack old codes, and build new ones. They may accelerate artificial intelligence, optimize global systems, or reveal new patterns in nature. But for now, they hum quietly in cold rooms, watched over by researchers who coax them forward with patience and care. Tiny machines, delicate and strange, yet filled with promise. These are the engines of tomorrow. And tonight, as you drift softly toward rest, you have walked through their long, gentle history, through the minds, dates, and discoveries that brought these unusual machines into being. The story is not over. But for now, it pauses here, in a quiet moment, letting the future unfold at its own pace.